I'm Jim Heffron. These are my lessons in Calculus 1, and we're doing the homeworks for the section on mean value theorem. Okay, so I'm going to take the opportunity of doing these homeworks. I often don't ask homeworks when I teach this in person. I'm going to take the opportunity of doing these homeworks to say that this is a point in the semester when, in my experience, point in the class where people often start to slide a little bit. I mean, the excitement of the beginning of the semester has passed, and there's all kinds of things to do. Papers start being due, programs start being due, readings start being due. So people start to feel that their schedule is getting filled up, and it's it's just getting to be a busier time. Fair enough, but again, the lesson is in mathematics is that the people who succeed, the people who get B's, can we make up a criteria like that? The people who succeed are the people who come to class and do the homework. In short, the people who just keep working at it. That in order to do well, you need to do the homeworks. Of course, to do the homeworks, you need to understand what you're doing, but nonetheless, you have to be doing the problem. So if you say, well, I'll just look, I thought it was pretty easy. No, you have to do them in number 1, number 3, number 5, number 7. That's how you get better. There's no shortcut. So, sorry. Okay. All right, let's start in. So as I said, I often, when I teach this in person, I often don't do any homework questions at all, don't assign any homework questions at all. But here, I just wanted to take a couple of opportunities. One of them is, of course, to go through and do an old one. So let's see if I can click. There we go. Go through and do an old one. So the one that I picked out was number 29. It says, take the derivative of r of t equals 2 square roots of t. This is from section 3.4, and I keep trying to remember to give the book credit. This is a Stewart Calculus book, edition 9. So 10 raised to the 2 square roots of t, number 29 here, 10 raised to the 2 square roots of t. So I'm taking the derivative. So chain rule, in short. It has been my experience that folks have a lot of trouble with chain rule. Now, if you're a person who doesn't have trouble with chain rule, instead, what gives you trouble is trigonometric functions, well, then you should be trying to do more of those if you can. Not to ignore chain rule, but sort of focus on. Okay, let's see. The derivative with respect to t of 10 raised to the 2 square roots of t. So it's a chain rule. There's a function of t. We're taking 2 square roots of t, and we're applying a function to it, 10 to the. So we've got to take the derivative of the 10 to the part and the derivative of the 2 square roots of t. Okay, the derivative of 10 to the is 10 to the times ln of 10. The derivative of the 2 square roots of t, we've done square root of t a lot. It's a t to the 1/2 power. So you get 2 times 1/2 t to the minus 1/2 power. Okay, and of course the 2 cancels with the 1/2, and you can clean it up a little bit, but maybe I'll just leave it like that. The point was to apply the chain rule, and we applied the chain rule. Okay, very good. So now I'm turning forward to the material that's new, section 4.2, having refreshed my memory on some older material. And I have down here numbers 5 through 8. I don't often ask even ones, but you see they come in a chunk here. So I thought the chunk was good. It says the graph of a function f is shown. Does f satisfy the hypotheses of the mean value theorem on the interval from 0 to 5? Okay, and if so, they suggest that you sketch in. So I'm going to turn the book here to the mean value theorem to remind you what the hypotheses are. Forgive me. There it is. There we go. F is continuous on the closed interval and differentiable on the open interval. So pretty small criteria, but continuous on the closed interval and differentiable on the open interval. Okay, so now we're flipping back to the problem. Oh, I have to slide again. There we go. So it says, does f satisfy the hypotheses? So continuous on the closed interval, 0, 1, 2, 3, 4, 5. I think so. Differentiable on the open interval. I don't think so. I think it does not have a derivative at x equals 3 because you got a sharp point there. So the answer is no, it does not satisfy the hypothesis of the mean value theorem on the interval. 6. continuous between 0 and 5, and again that's 1, 2, 3, 4, 5. They could have done me a favor by labeling the 5. So continuous on the closed interval, I think so. Differentiable on the open interval, not including the 0 and not including the 5. I think so. I think so. So then they want me to find a value C that satisfies the conclusion. So I think this is the average slope. Here's a line with the average slope, namely the average slope is 0. So I have to find an x star where the derivative is 0 at x star, and I guess I think I'm looking at right here. So that's x star equals 3. Okay, great. So now we are to number 7. It says continuous on the closed interval from 0 to 5. I think so. 1, 2, 3, 4, 5. I think so. Differentiable on the open interval between 0 and 5. Yes. So it has a derivative not at 5 but coming up to 5. So in the open interval that comes up to 5. Likewise, that's 0. So all I got to do then is pick out the average slope. Average slope is something like so. Okay, so that's a line with the average slope, and I just have to find an x star where the derivative is something like that. There we go. Maybe x star equals 4. You're looking at a tangent line like so. I think that's parallel to the line that connects the beginning and the end. Okay, great. And then here we go, the last one. We're looking for continuous on the closed interval from 0 to 5 and differentiable on the open interval from 0 to 5. And so again, I think continuous on the closed interval from 0 to 5, the answer is yes. Differentiable on the open interval from 0 to 5, I think not. I think that at x star equals 4, I'm not going to call it x star. At the input 4, I don't think there's a derivative there. I think the derivative's undefined. Okay, so because we have a sharp point. So we're looking at not differentiable, does not satisfy the conditions of the mean value theorem. So does not satisfy, does not satisfy. Okay, great. So that was 5 through 8. And then the last one that I was going to do was number 15. Again, try to slip it into the screen here. If I can. There we go, just barely fits. Okay, so it says verify that the function satisfies the hypothesis of the mean value theorem. Find all numbers lowercase c that satisfy the conclusion of the mean value theorem. And they gave me a function, it's 2x squared minus 3x plus 1. And it's not, there we go, 2x squared minus 3x plus 1. And the interval is from 0 to 2. So let's see. F of x is 2x squared minus 3x plus 1. And the intervals from 0 to 2, closed, of course, because the mean value theorem calls for it to be closed. Okay, sometimes I will write that as 0 dot dot 2. But the book follows what is really the standard notation, which is this. Okay, so continuous everywhere. There's no divided by 0 or square root of a negative number. So continuous everywhere and differentiable everywhere. So never mind open interval 0 to 2, differentiable everywhere. And then, of course, f prime of x is, 4x minus 3. Okay. Now they say find all numbers c that satisfy the conclusion of the mean value theorem. So I have to figure out what is the average slope. So I've got to find f of 0 and f of 2. F of 0 is obviously 1. How about f of 2? 2 times 4 minus 3 times 2 plus 1. So that's 8 minus 6 makes 2, and add 1 makes 3. Okay, so the average slope is 3 minus 1 over 2 minus 0, so that's 2 over 2 is 1. So that's the average slope. Okay, so I'm looking for where does f prime of x equal 1. So where in the range from 0 to 2 does f prime of x star equal 1. So of course I'm going to set 4x minus 3 equals 1. 4x minus 3 equals 1, and I get 4x equals 4. And if my calculations are right, I got x star equals 1, certainly in the range. Actually, I should point to the open interval. Certainly in the range. Okay? Okay, very good. Very good.